So, I'll be talking about really an introduction to parameterized algorithms and complexity, with first covering the very basics of algorithm design and hardness, and then spending about 20 minutes talking about some of the things that will be covered in this school, a bit from a bird's eye view. I have a question mark here, whether the talk is given by myself or not, and this is because our flight was scheduled to arrive yesterday at 2:30 a.m. It arrived something like 3:30, but there's also this strike that made it not certain whether we would be able to make it or not. So I'm happy to be here. So, what is the starting point for parameterized complexity? In many ways, it's NP-hardness. So, what do we know if your problem is NP-hard? Well, if it's NP-hard, then there is no algorithm that solves all the instances optimally in polynomial time. Right? However, if you are sitting there with some instances, you want to solve those, you don't care too much about the fact that there is no algorithm that solves all of them. All you want is to solve your instances. So hopefully your instances are the easy instances. So then the question is, well, is there some algorithm that solves the easy instances? And then you start thinking about it, and it's not entirely obvious, in fact, very much non-obvious, how to formally quantify what is an easy instance of a hard problem, or for that matter, an easy instance of an easy problem. Right? This is it's not necessarily an easy thing to do. So this is sort of one entry point into parameterized algorithms. And here is another one, maybe more the more standard one. Although both of these two are very standard views. In classical complexity, we measure the running time of our algorithms as a function of how big our input instance is. However, of course, when you make an algorithm, it's extremely rare that the bit size of the instance is the only thing that affects how fast your algorithm ends up running. And this has been recognized for a very, very long time. So for example, in the undergrad class, when you teach a BFS and a DFS, you don't actually tell how fast this search runs in terms of the bit size of the representation of your graph. You're saying, well, on a graph on n vertices and m edges, it takes order n plus m time. Yeah. Or in the same undergrad class where you teach an algorithm for subset sum, so here, this is the problem where I give you n integers and the target t, and I ask you, can you find a subset of these integers that add up to t? And then you teach a dynamic programming algorithm that runs in time n times t. Yeah? So already here you're seeing running time analysis that are in terms of not necessarily the input size and in terms of more than one parameter about the input. So other examples are, for example, the k-sat problem. The best known algorithms run in something like 2 to the power n into 1 minus 1 over k in the exponent. It's actually slightly more than 1 here, if I remember correctly. And of k-clique, the naive algorithm, so if I give you a graph G and an integer k, and I ask you, can I find k vertices so that every one of those is neighbor to everyone else? So k vertices, where they all are pairwise adjacent, you can do this easily in time n to the k plus 2. So these are many examples of algorithms and running time analysis where you end up measuring your running time in terms of more than one thing. And really, at this point, I would say somehow that the core philosophy of parameterized complexity is just measuring the running time in terms of more than one thing. And it somehow boils down to just that, somehow. However, so far, at least within the community of parameterized complexity and the tools that you're going to see in like 99% of the stuff that we will be talking about is about applied to NP-hard problems. So let's devise algorithms. Let's devise algorithms with running times that are measured in terms of the input size and something else. But let's focus on NP-hard problems. There will also be some focus on polynomial time algorithms and speeding those up in this school, but that's actually a pretty new development in parameterized algorithms. All right, so here's a first simple example, vertex cover. If I give you as input a graph G and an integer k, and then I ask you, can I find the vertex set of size at most k, such that every edge of the graph has at least one endpoint in this set S. So you're trying to cover all the edges using at most k vertices. And a set of vertices that covers all the edges in this sense is called a vertex cover. So now you're trying to find a vertex cover of size at most k. Well, you can easily do this in time 2 to the n by trying all subsets and checking whether this is a vertex cover and keeping the smallest one. And if you now use k, you know that you only need to look at the subsets of size at most k, and that ends up also taking something like big O of n to the k plus 2 time. Where is the plus 2 from? For each of the potential solutions you try, you go over all the edges, and then you check whether they have an endpoint outside of the or both endpoints outside of the vertex cover. So notice that this running time here is polynomial for every fixed value of k, right? So if I'm looking for a vertex cover of size 100, I can find it in time n to the power 102, which is polynomial. If I ask you to find the vertex cover of size 1000, I can also find it in polynomial time, n to the power 1002, right? So what happens is that if I have a problem with input size n and some parameter k, and for every fixed value of k, I can solve this problem in polynomial time, then I say that my algorithm is an XP algorithm. And the reason for this name is that it's slice-wise polynomial, and x, you're slicing. This is what I'm guessing. I think I asked. I mean, Mike Fellows is the one, and Rod Downey are the one who have given this name. I've heard them say slice-wise polynomial and XP, and this is my guess where this comes from. So notice that n to the k plus 2, or like n to the k, isn't the only kind of running time you can have for an XP algorithm. In fact, for any function f and any function g, if you have an algorithm with running time f of k times n to the g of k, then that's a slice-wise polynomial time algorithm, right? So I could devise an algorithm with running time log k times n to the 2 to the 2 to the k, and for every fixed value of k, this would still be polynomial. Okay, so whenever you have an algorithm, the next obvious question is, can you do better? Yes, and like Bob the Builder, yes, we can. So this is Sam Buss, around 93 or a little bit before that. He gave the following cute argument for how to do vertex cover in better than n to the k time. So the bottleneck is in this n to the k algorithm is really that you're trying all possibilities. So if you can identify some vertices that has to go into the solution, well, then you have fewer possibilities to try. So here is a simple observation. If I'm looking for a vertex cover of size k, and I find a vertex of degree k plus 1. Let's do it like this. So any vertex of degree k plus 1 has to be in the solution of size at most k if it exists. Why is that? Well, suppose I didn't put them in, then each of these edges need to be covered, yes? Solution is a vertex cover, I need to cover all the edges. So if I don't cover this edge from this side, I need to cover him from that side. Oh, I need to pick this vertex, this vertex, this vertex, okay, then I need to pick k plus 1 vertices, but I'm supposed to have a solution of size at most k, this doesn't work, so I conclude that this vertex has to be in the solution. Alright, once you've put the vertex into the vertex cover, now automatically all of these edges get covered. Yeah? And once all of these edges get covered, they don't have any function anymore, so I can just delete the vertex and all the incident edges and decrease my budget by k because by 1 because I put one vertex into the solution. Now on the other hand, if I find a vertex that isn't incident to any edges, then I can just remove it because it isn't doing anything anyway without putting them in my solution. All right, so I keep doing this for as long as I can and end up in the following situation. Every vertex has degree at most k, because if I had a vertex of degree strictly more than k, I would have put them into the solution and removed them and decreased k by 1 and continued. Fine. And the second thing is, if at this point I have at least k squared plus 1 edges left in the graph, I can say, no, my graph does not have a vertex cover of size at most k. Why is that? Well, I'm trying to cover k squared plus 1 edges with k vertices, and every vertex can only cover k edges because it has degree at most k. So if one vertex can cover at most k edges, then k vertices can cover at most k square edges, and if there is k squared plus one of them has to go uncovered. All right. So if I have too many edges left, I can just say no right away, but then I have at most k square edges left. That implies that I have at most k square vertices left. Well, actually 2k squared, right? Because I could potentially have a matching. And then brute forcing, if I have 2k square vertices, then n to the power k is 2k to the power k, which is basically like k to the power k. Yeah? So brute forcing now takes time k to the power k, and if you're careful about how you implement these reduction rules, you can implement them in linear time. That's a nice exercise, how to implement these reduction rules exhaustively in linear time, and you get this sort of running time. Now, if you try plugging in, just for an idea of how much of an improvement this is, if you try plugging in something like n equals 10,000 and k equal to 10, so suppose I give you a graph with 10,000 vertices and edges, and I want to find the vertex cover of size 10, then the n to the k algorithm is not going to terminate within the lifetime of the universe, whereas this one, if you buy all of the computing power of Google and you run this algorithm, and you can run this in parallel, then you would probably terminate within a day or so. Yeah. So it's still really slow, but at least if you really wanted to solve your vertex cover instance, you could do it. Okay. So now the question is, can you do even better? And again, the answer is yes, we can. But using a slightly different approach. So let's consider an edge. Let's call it UV. Well, what are we trying to do? We're trying to pick vertices such that for every edge, at least one of the two endpoints is in the vertex cover. So one of these two endpoints better be in the vertex cover. Yeah? All right, so at least one of them must be in the solution. And that means that G has a vertex cover of size k if and only if either G minus U has a vertex cover of size at most k minus 1, or G minus V has a vertex cover of size at most k minus 1. So the first case is the case when there exists an optimal solution in G containing U. Right? Okay, so now this sort of naturally gives rise to a recursive algorithm. Right? You just run, in order to solve G comma k, you run your algorithm G minus U, k minus 1, and G minus V, k minus 1. If either one of them returns yes, you answer yes. So what's the running time of this algorithm? Well, if you draw the recursion tree, then you start out with one instance with parameter k, so the solution size that you're looking for. Then you're going to create two instances with parameter k minus 1. Each of those will create two instances of parameter k minus 2, and so on. Yes? So after, at depth k, you're going to have 2 to the k instances where you're looking for a vertex cover of size 0. But looking for a vertex cover of size 0 is easy. If your graph has any edges, then you answer no. If your graph has no edges, you answer yes. Yeah? So in particular, you end up having an algorithm that spends linear time in each recursion step, and there is 2 to the k leaves in the tree, so the total running time ends up being 2 to the power k, and to the c, in fact, this term is linear, right? It's n plus m. So this algorithm was discovered by Downey and Fellows in the early 90s. In fact, vertex cover has an interesting history where this algorithm was discovered, and then there was a 3 to the k algorithm published in either Stock or Fox, and then this algorithm was discovered again. While this looks easy in retrospect, at least like 25 years ago, I guess it wasn't. Yeah? So one more thing that I could mention is that the two methods, the one that gave the k to the k algorithm and the one that gave a 2 to the k algorithm, can actually be combined to give you something better. Because the first one had a nice form on the running time. It had n plus m plus some function of k, k to the k. And the next one had a better dependence on k. It was 2 to the k, but it was 2 to the k times a polynomial. And then the question is, can you get the best of both worlds? Can you get 2 to the k dependence on the parameter, but plus linear time in the input rather than times? And of course, just by combining the two ideas, you automatically get this. Because what is it we did? We started out with a graph and an integer k and asked, oh, can I find the vertex cover of size at most k? And in polynomial time, by just picking vertices of high degree into our solution, we produced in linear time an instance g prime and k prime, so that where k prime was at most k, because we only decreased the budget when we were picking things into the solution, and where the number of edges was at most 2k square, such that this thing is a yes instance if and only if our original instance is a yes instance. And now, instead of brute forcing this instance, of course, we can run the 2 to the k algorithm on it. So if we run the 2 to the k and to the c algorithm on this instance of size 2k squared, well, then you get an algorithm with running time n plus m plus 2 to the k times k to the c. And this will work in a few seconds on your phone. Yes, or actually no, it is a few milliseconds on your phone, right? With n equal to 1000 and k equal to 10. Okay, so let's recap. We looked at the same problem, namely vertex cover, and we gave 3 algorithms for it. One with running time n to the k, one with running time 2 to the k n plus m, and one with running time n plus m plus 2 to the k squared. And these were significantly faster than that one, even though already the first one was polynomial time for every fixed value of k. Now, somehow, a nice qualitative difference between the first running time and the second two is that here, in the second two, for every fixed value of k, you have the same polynomial running time. So for k equal to 100, this is linear time. For k equal to 1,000, this is linear time. For k equal to 10,000, it's still linear time. Yeah? So whenever you have this effect, that for every fixed value of k, you have the same exponent of the polynomial in the running time, this is what you call fixed parameter tractable. And I think this name is slightly confusing because fixed parameter tractable sort of suggests polynomial for every fixed value of k. But once and for all, remember that that's not what it means. It means the same polynomial for every fixed value of k. Yeah? Whereas the other one, polynomial for every fixed value of k, is n to the k plus 2. So another thing that you can, now that you're here, let me educate you and remember. So FPT is not the same as FTP, right? So FTP is file transfer protocol, and FPT is fixed parameter tractable. So I can't count how many review reports I've gotten saying that the paper gives a FTP algorithm for this problem. And I always want to write back and say that no, this is file transfer protocol. Anyway, so we have these three algorithms, and we said that whatever is on the left is sort of bad, whatever is on the right is sort of good. That's what we want. But we have two running times here that look qualitatively different, right? So we have f of k times n to the c, and then we have f of k plus n to the c, and then we ask ourselves, like why did we define FPT to be this one and not that one, right? We could be hoping for something even better of running time, f of k plus n to the c, which we actually managed to do for Vertex cover right now. Well, I claim that all problems that can be solved in time f of k n to the c can also be solved in time f of k plus n to the c, but for a different c and different f of k. So of course, one direction is easy, right? I mean, f of k plus n to the c is at most f of k times n to the c. Yeah? But what about the other direction? So if I have f of k times n to the c, how do I make an algorithm that runs in time at most some g of k times or plus some n to the c prime? The same algorithm works because a times b is at most a squared plus b squared. Yeah, it's a stupid trick. So f of k times n to the c is at most f of k squared plus n to the c squared, because one of these two terms is the biggest. Yeah, so you just keep the biggest one. Right. So in particular, there is no point in trying to define your own little complexity class for the problems that can be solved in time f of k plus n to the c, because that and f of k n to the c is actually the same thing, called FTP. Yeah? Okay.
I guess if you get away with it, you get two papers out of it. You find the first one and a surprising equivalence between two well-known classes in the second.
So I will at some point I can tell a story about something that we have done that sort of looks like that. Not quite like this, but actually not too far away from it. All right. Anyway, so here is a very naive question: are all problems slice-wise polynomial, or even better, are all problems FPT? So let me give you a simple, convincing no answer. Well, okay, the halting problem is probably not FPT because it's not even decidable, right? But is everything decidable FPT or XP? Well, let's look at graph coloring. So what's the graph coloring problem? I give you as input a graph G and an integer k, and I ask you, can I assign to every vertex a number, an integer from 1 to k, so that every edge has different numbered endpoints? Or can I color the vertices of a graph with k different colors, so that every edge has different colored endpoints? This is what is known as properly k-colorable, and I'm sure that you know that 3 coloring is already NP-complete. So it's already NP-complete to decide whether you can color the graph with 3 colors, such that every edge has different colored endpoints. Now, silly question, is k coloring XP? So does it have an f of k n to the g of k algorithm? Well, no, right? Because put in k equal to 3, and an XP algorithm would actually be polynomial for k equal to 3. XP is somehow, by definition, polynomial time for every fixed value of k. Yeah? So in particular, an XP algorithm for graph coloring would imply that p is equal to NP, which we don't really expect happening anytime soon. So it's safe to believe that coloring probably isn't even in XP. So this is our picture so far. So we have this class of all problems that are FBT, the class of all problems that are in XP, and we managed to put vertex cover inside FBT and graph coloring outside of XP. And now the next sort of natural question is, well, is there anything in between FBT and XP? So are there problems that are polynomial time solvable for every fixed value of k, but not solvable in time f of k and to the c? And again, here the sort of silly answer is yes, because of, for example, the time hierarchy theorem. But by parameterizing some crazy problems in crazy ways, you can actually prove unconditionally that there are things that are here and not there. Yes? But somehow the more interesting question is, if you have some particular problem that you're looking at, is this problem here, here, or here? Okay, you can put it here by making an algorithm. You can put it here by proving that it is NP-complete for k equal to 10. But if it is here, how do you prove or justify that it's probably not here? So here is an example. Let's look at the independent set problem. If I give you a graph G and an integer k, and I ask you, can I find a set of at least k vertices, or exactly k vertices, so that no pair of these vertices are adjacent? So this is called an independent set. It's an XP because, again, I can run an algorithm in time n to the k squared, just try everything. And we don't really believe that this problem is FBT, but how do you prove or justify it? And this is the complexity theory that was built by Downey and fellows in the early 90s, somehow in an analog of the philosophy behind NP-completeness. So let me quickly recap to you the philosophy behind NP-completeness. So, okay, here we have the classes, everything solvable in polynomial time, and exp time, so everything solvable in time 2 to the poly n. And we have some problem that we think is here, but we want to justify. Right? We want to justify that independent set is probably not here. So for many problems, such as independent sets, they're actually inside this smaller class of exp time that is NP. And there is this set of problems that we call NP-complete, so that if any one of these guys ends up being polynomial time solvable, then these two classes are actually the same. For some philosophical reasons, we believe that those two classes are not actually the same, so therefore we believe that whatever is NP-complete actually is not inside P. Yeah? So this is the very brief idea of NP-completeness that I'm sure you've already have seen and probably already taught several times. So let's do the same thing in parameterized complexity with FBT playing the role of P and XP playing the role of exp time. Yeah? So you want to look at some particular problem, for example, independent set, and you would like to show that, well, it's probably not in FPT. And the way you do that is that you define some complexity class called W1, whatever that is. Just think of that as the parameterized analog of NP. Then you find some complete problems in that class under the appropriate notion of reductions. That's your analog to NP completeness, so you does W1 complete, and then you prove that independent set is, in fact, W1 complete. And if you buy the argumentation that, well, you don't actually believe that these two classes are the same, well, you've now just justified that independent set is probably not FPT. Yeah? And this is what was done by Downey and Fellows. So in this talk, we're actually just going to use the fact that independent set is probably not FPT and derive some ideas from there. So usually in NP completeness, you actually end up showing NP completeness. Whereas in parameterized complexity, you often end up looking at problems that aren't in W1, and what you want is actually the analog of NP hardness, which ends up being W1 hardness. Okay? All right. So this is a very simplified research flowchart of parameterized complexity. You start out with your problem and you ask, okay, is it even XP? And then either your answer is nope, it's NP complete for k equal to 10, and then you're sad, because then you don't know what to do else, you pick a different problem. Or the answer is yes, yeah, and it is FPT. No, yes, it is XP. So then the next question is it FPT? And now you have that means both to answer yes and no. Either you answer no, it's W hard, and then you again are sad and you look at another problem, yeah? Or you find an algorithm, yes, it's FPT, and you're happy, but again you're done and you have to look for another problem. Yeah? So this is the really, really simplified flowchart of how to do research in parameterized complexity, at least in the early 90s. Okay? But the world has come a long way from then, and let me try to move you through the motions. So first, how do you show W hardness? So let's look at the Clique problem, right? If I give you a graph G in integer k and I ask you, is there a set of vertices of size at least k where every pair of these vertices is adjacent? Well, you have an algorithm with running time basically n to the k. And then the question is this problem FPT? Well, let's prove that it is W1 hard under the assumption that independent set is W1 hard, or W1 complete. So what does it mean to prove that Clique is W1 hard? It means to prove that if Clique was FPT, then W1 would be equal to FPT. And we just said that we can just assume that independent set is W1 complete. So it's enough to prove that if Clique was FPT, then independent set would be FPT as well. And this isn't very difficult, right? All we need to do is, given an FPT algorithm for Clique, we need to design an FPT algorithm for independent set. Okay, so given an instance, gk of Clique, here we're interested, does this graph have a k-clique? I just complement the graph. So this is a bar, this is an overline, right? It should be up here. Okay? So you complement the graph, you change all the edges into non-edges, all the non-edges into edges, and now a clique turns into an independent set. Yeah? So this complement graph has an independent... if I wanted to solve independent set, I would complement it, and then independent sets turn into cliques. I would run my clique algorithm in time f of k n to the c, and if I find a clique, well, that's an independent set in my original graph. Yeah? So now an f of k times n to the c algorithm for Clique turns into an f of k n to the c algorithm for independent set. So if Clique was FPT, then independent set would be as well. Yeah? And what did we use to show that? Well, just the NP completeness reduction you already know. Just complement the graph. Okay, but I'm sure you also know an NP completeness reduction from independent set to vertex cover. Yeah? So doesn't that mean that the vertex cover is also W1 hard? So, okay, can we reduce independent set to vertex cover so that an f of k n to the c algorithm for vertex cover would give us such an algorithm for independent set? Well, what is it we know, right? If I have an independent set of size k, then the rest of the vertices form a vertex cover. If I have a vertex cover, then the rest of the vertices form an independent set. So in particular, G has an independent set of size at least k, if and only if G has a vertex cover of size at most n minus k. Right? If I have a set of size k, then the rest of the vertices have size n minus k. So if I have, oh wait, I actually do have an algorithm for vertex cover running time 2 to the k plus n plus m. Yeah? So what kind of algorithm does that give me for independent set? Well, to solve an instance G comma k for independent set, then I need to solve vertex cover with parameter n minus k. So I get a 2 to the n minus k algorithm for independent set, which is not FPT at all. Right? This is not f of k times n to the c. Yeah? So notice that the NP completeness reduction from independent set to vertex cover blows up the parameter k. And that does not preserve FPT-ness. Yeah? So when you're doing reductions to prove W hardness, what you need to make sure is that in addition to running time and preserving the answer, the new parameter should just be a function of the previous one. Okay. So we said that Clique is W1 hard, so it's probably not FPT. But what if I, instead of the parameter k, say that the parameter is the maximum degree of the input graph? So suppose I give you a graph G, and he has maximum degree delta, and then I ask you, can I find a set of size at most k such that every pair of vertices are adjacent? So it's still the same problem. Okay, so here is an algorithm. For every vertex v in the graph, look for the largest clique in his neighborhood. Because every clique is some vertex union the largest clique in the neighborhood of that vertex. But for every vertex, his size of the neighborhood is at most delta. So the running time is 2 to the power delta times n, yeah? Where delta is the maximum degree. And so for every fixed value of delta, this is actually linear time, yeah? So if delta is your parameter, then this is fixed parameter tractable. Okay, we just said Clique is probably not fixed parameter tractable, and then we said Clique is fixed parameter tractable. What on earth is happening here? Yeah, there's something funny. Well, what we did was that we showed that it is not fixed parameter tractable with one parameter, and fixed parameter tractable with another one, and those two are perfectly consistent. So when we say that Clique is W1 hard, what we actually mean is that there is probably no f of k times n to the c time algorithm for it, where k is the solution size we're looking for. So this is just a sloppy way of saying that Clique parameterized by solution size k is W1 hard. Yeah? On the other hand, when we have an algorithm with running time 2 to the delta, then what this means is that Clique parameterized by maximum degree is fixed parameter tractable. So whenever you're saying that some problem is W1 hard or FPT, you really should be careful about specifying it's a problem parameterized by something is either W1 hard or FPT, because once you change the something, it actually also might change the outcome. Yeah? So for every problem, there's many different ways of parameterizing the same problem, and there's no single way that is always the right one. So for a while, at least when I was a grad student, I would always look in the definition of, say, NP-complete problems, and I would look for a k in the definition. And like whatever was the k, I would try to parameterize by that. And if it wasn't k, then I couldn't parameterize it by it because it's f of k n to the c. And I mean, you're laughing now, but this is actually not too far from the truth. I mean, if I wanted to use something different than k as a parameter, I would sort of feel uncomfortable. It's just like, what is happening? It should be f of k. Yeah? But now the field has come a bit further. You're free to use other letters as parameters. It's okay. Okay, so for future talks, I also want to introduce you to the formal definition of parameterized problems. So formally, just as decision problems are a subset of sigma star, and an algorithm for one tries to decide whether a particular string is in this subset or not, a parameterized problem is a subset of sigma star times n. So every instance is a string and a number, and the job of the algorithm is to decide, is this yes or no? Yeah? And you specify the set of such pairs that are yes instances. So Clique, parameterized by solution size, is the set of all pairs s comma k, where s encodes a graph, and the graph has a clique of size at least k. That's easy enough. Now, Clique parameterized by max degree is a little bit trickier. So it's s and a degree, and then the yes instances are the ones where s encodes a graph and an integer k, and g has maximum degree at most delta and a clique of size at least k. Okay, so if this is a little bit confusing, don't despair, but sit down on your own time and try to formulate 3 or 4 different parameterized decision problems, and I'm sure you'll get the hang of it. So this is our research flowchart, and then the question is this the end? Well, no, it's not the end, because this is the end for one parameterization of the problem. So notice we've now said that coloring parameterized by the number of colors, not even xp. Independent set and clique parameterized by solution size are xp and w hard, and vertex cover parameterized by solution size is fpt. But now we can ask, well, what if we try with a new parameter? Right? What if we try clique parameterized by something else? Oh, parameterized by delta. Ah, yeah, this time it actually turned out to be fpt. This is precisely what we did. So now we can do the same, for example, with graph coloring, pick a new parameter for that, but also in the case when we have success. So also in the case when we have a parameterized algorithm, we can try finding a FBT algorithm with a new and smaller parameter, because if you think about it, you have algorithms with running time f of parameter n to the c. Yeah? If you're able to get an algorithm with f of another parameter n to the c, with a parameter that is always smaller, and you get the same f, then you actually have a better algorithm, right? So you can try a new parameter both when you succeeded and found an algorithm, or failed and got a hardness proof. So here is a first example. Look at coloring parameterized by vertex cover. All right, I have something like 15 minutes? 10 minutes, okay. Let's look at coloring parameterized by vertex cover. So if I give you a graph G and an integer k, and I ask you, and I tell you that x is a vertex cover of the graph, and my parameter is the size of this vertex cover, and now I ask you, does G have a k coloring? So now, if my parameter is the size of the vertex cover, fpt actually means f of x poly n. Yeah? So can we get such an algorithm? Well, this is sort of what our graph looks like. We have a vertex cover x, and then we have the rest, and the rest is an independent set. So now I claim that x plus 1 colors is always enough, because I can color all of these vertices with different colors, and then use the last color for the entire independent set. And that's a proper coloring of the graph. So in particular, if my budget for a number of colors is more than x plus 1, I just say yes. So now I can assume that k is at most x. Yeah? So now I can branch on all of the possible ways of coloring my vertex cover. There's k to the x, so at most x to the x ways of doing that. And for each of those ways, I can just color my independent set greedily. Look at every vertex and say, oh, do I have a free color to color him? Well, color him with that. Yeah? And notice that this actually takes at k to the x times linear, so x to the x takes n plus m time. So now we found a simple different parameterization for graph coloring, which actually turned out to be FPT. Now, what about vertex cover? This we found out to be FPT. Here is an interesting parameter. You know that the size of a vertex cover in any graph has to be at least the maximum matching in that graph. So matching is a collection of edges that don't share any endpoints. Yeah? So if I have a matching of size k, then definitely I need to have a vertex cover of size k because I need to pick one vertex from each of the matching edges. Yeah? So now you can ask yourself, well, this parameter can be really small, even when k, the size of the solution, is quite big. So now you ask yourself, is it possible to find an algorithm with running time f of k minus the size of the maximum matching times n to the c? So notice that this in particular means that finding a vertex cover of size equal to maximum matching should be polynomial time solvable. And this is actually exactly recognizing Koenig graphs, right? So it's possible to generalize this, and for every fixed difference between maximum matching and k, you can actually solve this in the same polynomial time. Yeah? I'm not going to go there. I think this will be covered in one of the talks later in this school. So this gives us the following new research flowchart with the following additional results. Okay, is this the end? Well, for independent set, we know that we have an algorithm running time n to the k, and we have a lower bound that says that there is no algorithm with running time f of k n to the c. But there is still a huge gap between the upper and lower bound, right? So it's still, we could still potentially find a lot faster algorithms for independent set without meeting this lower bound. And this has actually been done back in 1985, right? It's before W hardness even, right? So they found an algorithm that solves independent set in n to the omega k over 3, where omega is the matrix multiplication constant. So today this running time is n to the 0.79 k. And where does this omega come from? So the hint is that if you want to find a triangle, it's enough to look at the adjacency matrix of the graph, take it to the power cubed, and see if any of the diagonal entries is non-zero or not. Yeah. If you haven't seen this, it's a nice thing to try to look at. I'm not going to go there in more detail. I have like 5 minutes left, right? Okay, what about faster vertex cover? Well, we have an algorithm with running time 2 to the k, and we know that we don't have a polynomial time algorithm unless p is equal to np, so still there is gigantic room for improvement. And in fact, in the next lecture, Fedor is going to show you a 1.47 to the k algorithm. And in fact, you can even do better. You can do 1.27 to the power k. And for all we know, you can do even better here. Yes? So the new research flowchart becomes that once you come to an XP algorithm, or like if you're W hard in XP, what you try to do is to just get better and better XP algorithms. If you have an FPT algorithm, you try getting better and better FPT algorithms. Okay, but can we then just keep improving, right? I mean, can I go, if we manage n to the 0.79, could I maybe manage n to the 0.1k, n to the 0.001k, or n to the square root of k? And the same for vertex cover, right? Could I, instead of 1.47 to the k, get 1.000001 to the power k? Or even 2 to the square root k? Well, these three clever people, Implagleazzo, Paturi, and Zane, made a really nice hypothesis called the exponential time hypothesis. And that is that there exists an epsilon greater than 0, such that 3sat with n variables needs 2 to the power epsilon n time. Yeah? So there exists some number of zeros so that 3sat needs at least 1.00001 to the n time. Yeah? And the reason this conjecture is so clever is because it ends up being surprisingly useful for throwing tight lower bounds. So very often, when you're not able to make progress, you're able to show that if you made more progress, you would actually violate this conjecture. For example, we have the vertex cover algorithm that runs in time 1.20 something to the k, and we cannot improve it to arbitrarily large number of zeros, assuming ETH. Or, and you show that just tracing the NP completeness reduction. Or for independent set, we have an algorithm with running time n.0.79k, and assuming ETH, we cannot improve this to an arbitrarily small constant in the exponent. Now, we have an algorithm with running time x to the x for graph coloring, and assuming ETH, you cannot improve that to x to the power 0.00001x either. Yeah? So, it's very often that whenever you have some algorithm and you're not able to improve it, actually it turns out that under ETH, you can't improve it very much. Now, what do we mean by very much? Look, all of these lower bounds are on the form exists epsilon, so that there is no algorithm with running time 2 to the epsilon something something. Yeah? So, in particular, this epsilon is purely existential. You can make it as small as you want. So the problem is that we cannot distinguish between 2 to the k algorithms and 1.99 to the k algorithms because the epsilon would just fudge that. Yes? For that you need stronger conjectures, say like the strong ETH, and we're going to cover that in this school as well, but I'm not going to talk about that. There's a lot more to come, and some of these things will show up in this school and some will not, but I just wanted to flash you some buzzwords so that you get the feeling that there is actually more to the field than whatever I've been talking about so far. All right, thanks.